distinguished authorities and coordinator who had made this initiative possible. Respected Professor Narayan, the list includes respected Professor Narayan Prasad Padi, who is the chairman of the EICT Academy and the director of MNIT Jaipur, who is continuously supporting us to running this QT series at MNIT Jaipur. Respected Professor Vinit Sahula sir, who is the Chief Investigator of EICT Academy MNIT Jaipur, for motivating us for running this QT-06 course. Then Dr. Satya Sai Jagannath Nanda, who is the coordinator of EICT Academy, and our respected co-chief investigator, Professor Love Bhargav, Professor Pillai, sir. He don't need any introduction, and we call him the charm of QT series at MNIT Jaipur. And along with him, Dr. Ravi Kumar Madila, sir. Our principal coordinator, Dr. Rajendra Mitrabal, is here with us, connected offline. I also warm welcome to our eminent speakers and experts who will be guiding us throughout this journey. So briefly, Professor Arnav Kumar De, Professor Yash Vaswada from Dhirubhai Ambani University, Dr. Harish Sahu, who is a scientist of DRDO, and Professor Sandeep Kumar Singh from the Center of Photonics and Quantum Communication, IIT Roorkee. The brief introduction of our eminent speakers of the QT-06 will be given by Dr. Rajendra Mitrwal later. I'm happy to announce that we have total registered participants for this QT-06 course is crossing 1,000 plus participants, and still they are increasing, they are requesting us. We are truly honored to have such an esteemed panel of the academician, scientists, and the researcher with us today, who is connected online as well as offline. Now let me make a pause here and moment to introduce the QT-06 quantum communication course briefly. This program is a part of the AICTE approved minor course curriculum on the quantum computing, which is jointly supported by AICTE, DST, and IBM. It is the sixth in the QT series of the faculty development program designed to provide 20 days of the intensive training with the 40 hours of the expert session in online mode. The modules of these programs have been carefully structured to cover both the fundamentals and the advanced aspects of the quantum communication. We will begin with the foundations of the optical physics, which includes polarization optics, light-matter interaction, and optical devices. Moving ahead, we will explore classical communication theory, which will cover the detectors, modulation techniques, and information theory. The heart of this program lies in the quantum communication, where we will learn about the quantum information, qubits, superposition, measurements, and quantum dense coding. Finally, we will delve into the quantum networks, addressing the futuristic concepts like quantum internet, satellite-based and fiber optic quantum communication, and emerging quantum hardware. This program is designed not just to build the knowledge, but also to inspire future collaboration and innovation in the exciting domain. As we all know, quantum communication stands at the frontier of the secure information transfer and next generation technology. Through this training, we aim to empower faculty members, doctoral researchers, and the professionals to contribute actively to the growing field. In conclusion, I once again extend my warmest welcome to all the dignitaries, experts, and the participants, and I'm confident that the coming session will be highly enriching, interactive, and intellectually stimulating. So let us embark on this exciting journey together and make QT-06 serve as a stepping stone towards the building India's capability in quantum technologies and communication. Thank you. Now I would like to request Dr. Rajendra Mitrwal to introduce the eminent speakers for the QT-06 course.
So I'll be sharing slides which will give you an introduction to the schedule as well as the speakers which will be presenting their thoughts throughout this FCP. So give me a moment. All right, so this is the inaugural sessions, and basically we at MNIT Jaipur, we are the coordinators, Dr. Kavita Lalwani and myself, Dr. Rajendra Mitharwal. And this is our first speaker, who is Professor Arnab Kumar Ray, who is actually a professor at Dhirubhai Ambani University in Gandhinagar, Gujarat. He holds a PhD in astrophysical fluid dynamics. He is going to give you an introduction to the polarization optics, which is needed in the case of quantum communication. So basically, he'll be giving you almost 5 sessions on this basics of the polarization optics, followed by Professor Yash Vasavada, who is actually is also a dean research at the same Dhirubhai Ambani University, and basically he holds PhD and MS degree from Virginia Tech in USA, and he's going to give you a basic of digital communication and information theory, which will be required to understand the more complicated concepts related to quantum communication. So he'll be giving almost around 7 lectures on the basics of digital communication and information theory. Followed by Dr. Mostafizur Rahman, who is actually a research scientist at IBM Research Lab, basically dealing with quantum technology. And he has done his PhD from IIT Kharagpur, and basically he has been working on all quantum algorithms. So he'll be giving 4 sessions related to quantum information theory. Next is Professor Aswat Babu, who is basically faculty at IIIT Dharwad, and he holds PhD in physics from IIT Kanpur, and basically specializes in 3 research areas: quantum optics, quantum information theory. So he's also going to talk about quantum memories and quantum repeaters. So there are 2 sessions. Sorry, these are 2 sessions, but they are of 3 hours. So basically, he'll be giving you 3 sessions on quantum memories and quantum repeaters. Followed by Dr. Anindita Banerjee, who is actually a principal scientist at CDAC Pune, and she is basically the research area is her expertise is in quantum information and computation. She holds PhD in physics from University of Pune, and she is also one of the key members who was involved in designing the model curriculum provided by AICT on quantum computing. Then we have Miss Nivedita De. She's currently pursuing PhD from University of Calcutta in the quantum computing, and her area is basically quantum computing and quantum algorithms. So she will be giving 2 sessions related to quantum key distributions. Followed by Miss Janani A. She's also a quantum engineer at IBM Quantum. And basically, she holds BS and MS degrees from IISER Pune, same in the area of physics. And she will be talking about post-quantum cryptography and quantum entanglements used in quantum communication. Then we have Dr. Harish Sau, who is a scientist at DRDO in New Delhi, and he holds PhD in cryptography from IIT Delhi. And he'll be basically dealing with these topics: quantum entanglement and measurements, quantum teleportation, quantum dense coding. Followed by Professor Sandeep Kumar Singh, who is actually faculty at IIT Roorkee in the Department of Electronics and Communication Engineering. He holds PhD degree in optical networks from Technical University of Braunschweig, Germany. And he's going to take 2 sessions, one on quantum internet and the other one on quantum networks. Followed by the stalwart of quantum computing in India, Professor R.P. Singh, who is currently a professor at Physical Research Laboratory, Ahmedabad. And he's going to talk about free space quantum communication in these 2 sessions on 8th September. Followed by, again, a research scholar, Sheikh Mohammed Abdullah bin Hanifa American, who is actually PhD student of Professor Alexander Ling, whose group has demonstrated the satellite-based communication in Singapore. So he's going to present his research group's work on 9th September, and the topics are satellite-based communication. And then we have Professor Bhaskar Kanseri, who is also one of the stalwarts in quantum computing in India. And basically, he's a professor at IIT Delhi in Department of Physics. And he has basically demonstrated quantum communication using fiber optics. So he'll be giving his he'll be presenting his research in fiber optic quantum communication on 10th September from 2 to 4 p.m. And the last sessions would be from another stalwart, who is Professor Anil Prabhakar, who is a professor at the Department of Electrical Engineering in IIT Madras. So he'll be giving the session, a general session on the application of quantum communication in India, and followed by a panel discussion with him and the other key speakers. So basically, this course, this FDP is being organized by various EICT academies. We have support from EICT Academy at IIT Kanpur, IIT Guwahati, NIT Patna, Triple ITDM Jabalpur. And we have been getting constant encouragement and mentoring from our Professor Vineet Sahula and Professor Emmanuel Pillai here at MNIT. And we are also being supported by research scholars Akshay Pratap Singh and Akshat Sharma. We also are grateful to our technical staff who have been working tirelessly for last few days and resolving the queries of different participants. They are Deepesh, Geeta, Ramesh, Babu, and Manish. So that's it from my side. Thank you.
Thank you very much, Rajendra sir, for giving the introduction on the eminent speakers and about the MNIT team. So now I would like to request Dr. Pillai, who is connected offline here with us. And just there were queries from the participant sides itself. When they join the WhatsApp group of the QT-06, they are asking me separately that what is the behind, should I join QT-05 to go to the QT-06, so and so. So I thought, why not we invite Pillai sir to give an overview on the QT0 series, which is started from 01 to till QT05 is finished. Now QT06 is today we are inaugurating. So sir will give the motive behind it and how they are related to the minor degree. So sir, now I'm handing over to you.
Yeah, thank you, Dr. Prasad Lalwani, for this time, and thank you all the participants. It's a joy that all of you are here back for the fifth course, though it is numbered the QT06. We missed or we combined two courses, QT03 and 04, which was 04 having more of hardware and also simulations. So we took the simulations part into QT03 itself. So we are yet to conduct QT04, but anyway, welcome to this fifth series. So these courses has already been told to you that they are part of the AICTE and National Quantum Mission, Department of Science and Technology, CDAC, TCS, IBM. Many of the organizations have come together and they have built a syllabus comprising of 11 courses. Recently, one more course was also added, QT00. So totally about 12 courses covering the entire basics, foundations of quantum computing, taking up to the major 4 verticals, which are part of National Quantum Mission. National Quantum Mission's website, if you visit, there are 4 major verticals which are shown. The first one is quantum computing. The second one is quantum communication. The third one is quantum sensing and quantum sensing and metrology. And fourth one is quantum materials and quantum, the other one is quantum materials and devices. So these 4 verticals form the 4 major courses that are coming up. We finished the first one, quantum computing, and the second one that is going to start today is quantum communication. And so that is the sequence, and I will be happy to announce that we have always been telling that those who finish 5 courses of 3 credits each, some of you will be completing with this course. That will be 5 courses, 15 credits. So you will be receiving a certificate, PG diploma certificate, either from EICT Academy, or it will be a PG certificate from AICTE, which is still not yet confirmed. But the PG diploma from MNIT EICT Academy will be done. It is subject to one more additional requirement. That is, you will have to attend the lectures, which are offline lectures and interaction with the IBM team, and followed by an offline exam, which will actually test your prowess in the courses that you have attended. So please prepare for those who are attempting these exams who would like to come. We will shortly announce the dates. One is immediately after this course, sometime once we complete the weekend after that. If it's possible, then the next one will be in October without clashing with the holidays. So we will try to look at it that you will have a weekend. You will spend Friday, Saturday, Sunday. So accordingly, maybe either Friday, Saturday or Saturday, Sunday, you can come, and we will conduct a 1.5 day of interaction, and you will write the exam, and then we will later evaluate the papers and award the certificate accordingly. So that's what is this course all about, and this is actually a motivation only. Otherwise, each course has been uniquely planned, and a lot of effort has been gone into QT-06. There was a slight delay in handing over the brochures, in circulating this material, also because we want to put the list of speakers in place, and getting their confirmations took some time, and putting the schedule also took some time. And but then you have a wonderful team with you, as you already heard. So many big names. They've all done a lot of practical work, especially CDAC, IIT Delhi, IIT Madras, and we know that Professor Anil Prabhakar from IIT Madras is the vertical head in National Quantum Mission, the vertical that handles quantum communication. So he's the director of that vertical. So he's speaking to us is a real great achievement. We have an international speaker also, Sheikh Mohammed Abdullah bin Hanifa American. And we are happy that he will be speaking from Singapore. Of course, there will be a time zone difference, but still it's manageable because Singapore is not that far. But then he is one of the, what do you say, the leading expert in the world is Alexander Ling. And under him, he is doing PhD. We tried to get Alexander Ling for you, but yeah, fortunately, we are having Mr. Sheikh Mohammed to speak to us. And we have a series of speakers you already know, Mustafizur, Dr. Mustafizur Rahman, Dr. Nivedita. They have been doing great work. And Dr. Sandeep Kumar Singh also has international exposure, and he will share with you. So putting this program is a big effort, and please take it seriously. It is very easy to bluff the systems, bluff the protocols, or escape. But then at 500 rupees, you are getting a great information, and it is only 2 hours. If you really spend this valuable time, not for the certificate, but for the knowledge, and later we can actually contribute something to our country. So we have always been inspired to do something for our country. That's why we are putting all these efforts. So many speakers have given their consent. So I think we should take this course seriously. Hence, the attendance constraint will be there. So kindly be attentive to it. Of course, when you miss the lecture, you can attend on WebEx. We will record your attendance there, and we will consider that attendance. So YouTube, though the links will be there, attendance will not be taken from there. You'll have to log in back onto the WebEx and attend the lectures and view the lectures. It will be counted as attendance for you. So please note that and then take it forward. And of course, the quizzes, we still keep it at 40% to perform. Of course, 80% and above will get an excellent certificate. 60% and above will get a very good certificate. 40% and above will get a good certificate, and less than 40% will still get a satisfactory certificate. But then you should meet the attendance requirement to get a satisfactory certificate. So please keep these in mind, and don't worry about the quiz. The quiz is not in a fixed 30-minute slot. It's a 30-minute slot where you write 20 questions, but it is not, what do you say, in a fixed time of 30 minutes you have to take the exam. Usually the quizzes start at 4 o'clock, usually on after the class on a weekend, and then we will open it till Sunday evening. So Friday evening to Sunday evening, we'll keep the exams open. Any 30 minutes during this time, you can take the exam. So till midnight on Sunday, the quizzes will be open. So 3 Saturdays and Sundays, all the 3 Saturdays and Sundays that run in the course, you will have quizzes. The schedule will be released by Dr. Mitterwal. So I hope I have covered a lot of ground in a very short time. And of course, we are available on the WhatsApp group, and also for other participants, whoever have any queries, they will come back to us through their respective academies. You will have your respective WhatsApp groups like IIIT Jabalpur, IIT Kanpur. We have chief investigators joining from there, Professor Aparajita Oja and Professor B.V. Funny. And it's a privilege that we are all here today. And thank you very much for showing your trust and confidence on us and joining back repeatedly for so many programs. And today also we see more than 450 people, 470 people here with us. And thank you so much. Thank you, Dr. Kavita, for this time.
Writing us about the QT series and motivation for attending the classes. And beautiful, like I was not knowing that there are different categories of the certificates. So I think you must have motivated now to join each and every session. So now I would like to invite Professor Vinit Saula, who is the Chief Investigator of EICT Academy at MNIT Jaipur. Sir, welcome to, I request you to kindly address the audience.
Thank you, Dr. Kavita. I think it's my honor and pleasure to be with all of you. Such a galaxy of eminent speakers. First of all, thanks to all of them. Thanks to IBM for spearheading the idea, germinating the idea, and then actually being with us for all the 10 programs. It's a marathon, and I think they deserve the big thanks for that part. Dr. Pilli has been coordinating all this from our side, and I think it will be always be less if I thank him. So it will be little thanks to him. Whatever thanks I give to him. Thank you very much, Dr. Pilli. Dr. Mithrwal and Dr. Kavita, thanks a lot for jotting down the kind of threads for this program and coming out with the galaxy of like good speakers and a good number of participants this time. Again, I think they are crossing 1,000 that way. I also welcome other chief investigators and joint program coordinators from other academy. Professor B.V. Funny was here. I think he had something. Professor Funny and Professor Oja from IIIT and Jabalpur and joint PC from Jabalpur and one more from other academy. I would like to thank our director, Professor M.P. Padi Saab, for supporting all the way to run these programs, which actually invite about 1,000 participants each that way, and is serving the nation very well that way. And all thanks to all my staff in academy, especially Geeta, Ramesh, Deepesh, Munish, and our administrative staff in the institute that way. Thanks again, Dr. Mithrwal and Kavita, for inviting me. Please go ahead. Thank you very much. I think we may invite Professor Funny, Professor Oja, and other joint PCs from other academies. Professor Oja, are you there? Joint Principal Coordinator from Jabalpur. Our faculty colleague from NIT Patna. IIT Roorkee. Yeah. Thank you very much. Thank you, Kavita.
Okay.
Yes.
Okay, thank you very much, sir, for enlightening us for this program. So now we will take 10 minutes break, and then we will join after 10 minutes for the technical session. So let's say it is 2:31 now. We will connect at 2:40. Okay.
Yeah, we can continue the same link.
Yeah, we will. Yeah.
The link is active, and we'll just connect we'll start the next section within 10 minutes. Thank you.
Hello? Hello? Am I audible? Hello, Rajinder.
Hello.
Hello, Rajendra. You can hear me? Professor Rajendra
We
Mithalwal.
will start in 10 minutes. We have just given 10 minutes break.
Oh, okay. Fine. So I shall just, I mean, I'll be live, but we will start in 10 minutes, right? Fine.
Just a second. Yes. You were saying something?
I was saying that I'll just then sit back for a while. You can hear me clearly, I hope. That is most important.
Yes, we can hear you clearly.
Okay, fine. Thanks. So you just let me know when to start. I'm ready.
Okay.
Okay, fine.
उनसे पूछो वो कौन है यही सिटी है
हाँ. Sir, anyone is asking? Hello, can you hear me?
Yes, I can hear you.
Okay,
So
okay,
we
okay.
can start this session formally.
Yes, yes.
So I welcome you all to this first session of this FDP, which will be given by Professor Arnab Kumar Ray. Professor Arnab Kumar Ray is a professor at Dhirubhai Ambani University in Gandhinagar, Gujarat. He basically holds a PhD in astrophysical fluid dynamics from Jadavpur University, Kolkata. And his research spans astrophysical accretion fluid dynamics, nonlinear system with extended contributions to condensed matter physics, nuclear physics, complex system, and geophysics. Alongside his academic pursuits, Professor Ray has also gained industrial experience in seismic processing, which enriches his multidisciplinary perspective. He maintains a strong interest in curriculum design and innovative teaching methodologies, ensuring that his students are exposed not only to theoretical knowledge, but also to practical and problem-solving approaches. He has also been involved in mentoring school students for international physics Olympiads. At Dhirubhai Ambani University, he teaches a wide ranges of courses, including computational and numerical methods, econophysics, and multidisciplinary problem-solving techniques, reflecting both his broad expertise and commitment to cross-disciplinary learning. So I welcome Professor Arnab Kumar Ray.
Thank you. Thank you. I will just start sharing the presentation. Sorry, here. You can see the presentation now on screen.
Yes, we can see your screen.
Full screen you can see, I hope.
Yes, full screen.
Okay, okay. So so these are I thank you all for giving me this opportunity. And so today I shall discuss some basic theory pertaining to polarization. So I have got 5 lectures, out of which today I have 2. So in these first 2 lectures, I shall discuss the basic ideas of theoretical foundations of polarization. The notes that I hope all of you can see being projected full screen, these notes have been prepared from the textbooks of Jenkins and White, Fundamentals of Optics, Francis A. Jenkins and Harvey White. And then the other textbook is Optics by Eugene Hecht. So these 2 textbooks, I shall email you the names later. So Hecht and Jenkins and White. Now, polarization is is an optical phenomenon. So first, I'll just like to, since this is an FDP on quantum computation, I shall also make a brief reference to how polarization is relevant to quantum information. So first, let me just touch upon the basic principle of polarization. So light, as you all would know, is an electromagnetic wave, right? And as such, light lends itself to various wave-like phenomena such as interference, diffraction, and polarization. So here I have mentioned interference and diffraction uh, to establish the broader context of the wave nature of light. Now, any wave will display features of both interference and diffraction, but not all waves will show polarization. So it is light that is subject to polarization due to its transverse character. So this thing is theoretically understood from Maxwell's electromagnetic theory, whereby Maxwell was able to show that light was an electromagnetic wave, and then using Maxwell's equations in free space, one could show the wave character of light, the transverse wave character of light. For this, I refer you to the standard textbook of David Griffiths, where all this theoretical work is shown. So actually what Maxwell did was to bring light within the broader umbrella of electromagnetism. Electricity, magnetism, and light, they are all connected to one another as different facets of the same phenomenon, electromagnetism. So light is an electromagnetic wave. It is a transverse electromagnetic wave, and polarized. This thing can be theoretically shown from Maxwell's equations. Polarization proves this fact experimentally. So that is the importance of polarization in the context of optics. Optics being the study of light. Now the question is that in with regard to quantum computation or quantum information theory, where does polarization fit in? Well, the thing is that polarization occurs in various polarized states. I shall mention that shortly, get into that discussion in greater detail. So various polarization states can be used to encode quantum information, and these become the basis for qubits, as in quantum. Those are the units of information in quantum information theory. So that is where polarization becomes relevant. Of course, my task here would be to discuss the foundations of polarization, but be it understood that this thing has got a good deal of relevance for quantum information theory. So here, let us just briefly look at certain features of electromagnetism. At the top of page 2, I have written an equation. Z cap is proportional to E cross B. E being the electric field vector and B is the magnetic field vector. Now, light as an electromagnetic wave propagates through space due to the oscillations of these two vector fields. Now, if we imagine that in 3 space, E is oscillating, the electric field is oscillating along the x-axis, and the magnetic field B is oscillating along the y-axis. Both of these fields, by the way, are in phase. So when you have the maximum of one field, when the E field oscillates to its maximum, the B field will also oscillate to its maximum. When the E field goes down to zero, the B field will also go down to zero in the oscillation process. The only difference being that the electric field will be oscillating along the x direction, let us say, and the magnetic field will be oscillating along the y direction. So they are two faces of the same coin, twins actually, like conjoined twins, and they are locked to each other everlastingly. And this oscillation will produce the propagation of a wave through free space. Well, actually, through the electromagnetic field, and the direction of that propagation, let us say, is the z-axis, whose unit vector is z cap. So light is simply the a disturbance that propagates through the electromagnetic field continuum. So that is how light goes about. And let us say that the electric field is polarized along the plane of the xz plane, the x-axis. uh, E field is oscillating along the x-axis, B field is oscillating along the y-axis, and light is propagating along the z-axis. So the plane of polarization of the electric field is the xz plane, and the plane of polarization of the magnetic field is the yz plane. So here already you have some understanding of polarization, that you have two fields polarized with respect to each other at 90 degrees, orthogonal to each other, perpendicular to each other, and polarized, trapped in a particular plane. So here we are just to consider only the electric field. There's a question as to why we should do that. Why should we not worry about the magnetic field? Because for the simple reason that as soon as you work with the electric field, the magnetic field will also be fixed in space along its own plane of polarization. So we need to just worry about one field. The other field will not change its orientation with respect to the first field. So here we are just looking at the electric field. So here now let us look at this thing. Natural light is a superposition of many randomly oriented wave trains, so unpolarized. So when light comes out of a source, we are just worrying about the electric field polarization, like I mentioned to you. If the electric field is oscillating along the x-axis, then the magnetic field will be oscillating along an axis perpendicular to that. So usually we assign that direction to be y. So now, but when a light wave train leaves its source, it can have any plane of polarization, right? So natural light will be a mixture of various light wave trains randomly polarized in space, randomly oriented in space. So here I have drawn a schematic diagram of this situation. There are two axes, the dotted lines. The x-axis is along the horizontal direction, and the y-axis dotted line is along the vertical direction. And in between, you have a whole lot of arrows. The arrows are, so if you look at a light wave train approaching you, just like if you stand on a railway track and a train approaches you, you just see the train as a small, ideally assumed to be a point-like object, right? You just see the front face of the train. You don't see the train at side on through its entire length. So here it is, but the electric field, a train of course doesn't oscillate perpendicular to the direction of its propagation, but the electric field vector oscillates. So you will see the field vector. I hope you can all see the movement of my cursor. You will see the field vector oscillating up and down like that. So these are various random states of polarization. Let's say in the first quadrant, XY, there are two arrows pointing outwards, and 180 degrees opposite to these two arrows in the third quadrant, you will have two other arrows going in the completely opposite direction. So that is the polarized state that you're observing, the oscillation of the electric field that you're observing head on. So the two arrow heads are the maximum amplitudes of the oscillation. So the light wave is oscillating along this direction as it is approaching you. Similarly, there's another plane of polarization oscillating as it is approaching you. And likewise, this is a mixture of various planes of polarization in natural light, unpolarized light. Now, if by some means you are able to filter out or collapse all the planes of polarization, all the oscillatory planes, or along one fixed direction, then you would have achieved a polarized light beam. So let us now see, going back to the diagram at the bottom of page 2, every vector can be decomposed into its two components, two orthogonal components, one along the x-axis and one along the y-axis. So confining the orientation of the E field of oscillation, so all of these things could be collapsed along two directions. So every vector can be you can decompose it into two components, and thereafter what you will see is just two components oscillating, one along the horizontal axis, some of all the horizontal components and some of all the vertical components oscillating along the two directions. But now if by some means you can just filter out all the other states of all the other orientation states and manage to retain only one, confining the orientation of the E field oscillations along one direction only and filtering out all the other directions, is known as polarization. So this is how you achieve that. So here it is. So suppose we have achieved a polarization state. Now, how do we do that? We shall look at that later. So here is a certain state of polarization. You have the electric field oscillating along this plane of polarization, as you said. So this plane, look at this diagram. X is pointing in the horizontal direction, Y is pointing in the vertical direction, and X cross Y, the Z direction, is pointing towards you, which I have not drawn on this plane. So you're as if looking at the light beam head on as it is coming towards you. And this beam is confined to this one plane. The plane, as it has been represented on this page, is just collapsed to a line. But if you project that line in 3 space along the z-axis coming towards you, you can imagine the plane of polarization in this 3 space. So this is the plane, and the line that you have in this diagram is the transmission axis. So that is the axis that is filtering out the polarized state of light. So that's how you achieve that. Now you can very well ask me, how do I polarize that? One very standard way is to make light pass through a crystal lattice. A crystal lattice has got these atoms lined up one after the other, and between two sets of atomic planes, you have a little gap. So the plane of polarization that is aligned with that gap will filter through, and the other planes will be filtered out. So that is using a crystal lattice. You can filter out the undesirable planes of polarization and filter in only the desired plane that you want. So that transmission axis will be aligned with the gap in the between the atomic planes. So that is how you see it. So here it is. Now this plane of polarization has got an alignment of angle theta with the x-axis, and accordingly along the x-axis you have the x component of the electric field, that is Ex vector, and similarly along the vertical axis you have the y component of the electric field, that is the Ey vector. So Ex is equal to electric field E vector cos theta, and Ey will be equal to electric field E vector sine theta. Right. And so every polarized state can be viewed as the vector sum of these two orthogonal states along x and y. So addition of vectors will happen. So let us now look at the little mathematical discussion that follows here. Ex is equal to E naught x, which is the amplitude along the x-axis, cos kz minus omega t. So the light wave is propagating along the z-axis. The oscillation is happening along on the xy plane, and the vector field that is oscillating along on the xy plane has been decomposed into its x component and into its y component. So the x component we are writing as E naught x cosine kz minus omega t x cap, and Ey is equal to E naught y cosine kz minus omega t y cap. So kz minus omega t, this thing represents a traveling wave, the argument of the cosine function. And x cap, so Ex, this formula at the top of page 4 corresponds to this horizontal axis in this dotted axis in this diagram, and similarly Ey along the vertical axis. So when you add the two up, vector E is equal to vector sum of Ex plus vector sum of Ex and Ey. And so this is what you get, cosine kz E naught x cap plus E naught y cap. So this part, E naught x cap plus E naught y cap, is the fixed vector amplitude, and cosine kz minus omega t is the phase of the wave, that is scalar variable phase. So scalar variable phase and fixed amplitude vector. So fixed vector amplitude. Okay. So this is the state of a linearly polarized light or plane polarized light. Sometimes it can very well happen, that happens in the phenomenon of optical activity, that as the light passes through what is known as an optically active material, this plane of polarization starts rotating instead of being fixed. So that also we shall discuss. Hopefully we should have time for that. Optical activity is a very important phenomenon in biological systems. Like, for instance, amino acids are optically active substances. Sugar is an optically active substance. So those things display these polarizing behavior. So but for the time being, let's just uh, concentrate or focus on linearly polarized light or plane polarized light with a fixed oscillatory plane. So this is how it goes. So here is a slightly more detailed diagram. You have E naught x, x cap, E naught y cap vector as along this direction. This is the positive direction, positive amplitude. This is the negative end of the amplitude. The positive part will correspond to cosine phase going to 1, and the maximum of the negative part will correspond to the cosine phase going to -1. And here the wave will come down to 0. So that's, and this is the z direction. It is pointing towards you, crudely drawn in this page with this axis. I mean, you just imagine that it is going towards you. and this is the angle theta. So this is the how you get it. Okay, so here's the broader diagrammatic representation. Natural light before polarization, it's a mixture of various polarized states, and after polarization, only a select orientation is happening over here. So electric field is oriented along the allowed transmission axis of the polarization. Of course, you can very well ask me what will happen to the magnetic field. That will be at 90 degrees to this polarized state. Okay, so here is now what we shall do. We shall look at a few things. So suppose you have, I mean, basic formulae to work with. So here you have a certain polarized state of light represented by this dotted vector. That's the vector E. Now you make this, so light has been polarized, right? And now you make this polarized light pass through a polarizing material. So let us say it's some sort of a crystal material. A crystal is made up of various atomic planes, neatly layered one after the other. And between the atomic planes, you have gaps, right? So suppose you have aligned your crystal material in such a way that the gap exactly corresponds to this, the orientation of this dotted line. Then all of the polarized light will pass through that gap. But now you slowly start rotating the uh, polarizing crystal, or what actually it is known, the technical name is of that material, or that substance is known as analyzer. So you slowly rotate it. As you rotate it to greater and greater angle, let's say you've rotated it to 90 degrees, then it will be like this situation that you have a very narrow gap and a human being is trying to walk through that gap. If only the height of the human being is aligned with that gap, that person will be able to walk through that gap. But if you try to lie on your back and try to roll towards that gap, then nothing of that human being will pass through that gap. So here is also something like that. So this E state is like a human being, and all of it will pass through the crystal gap only when there is perfect alignment between the two. Suppose there is a 90-degree orthogonality between the analyzer and this electric field, then none of it will go through. And for intermediate angles, only a part of it will go through, and that part of it that filters through will have a curtailed electric vector field E prime, and the intensity of that will be I prime. E vector field, the corresponding intensity is I. E prime vector field, the corresponding intensity is I prime. So E prime is equal to E cos theta. And so the intensity is, I believe you are familiar with this thing. Intensity is the square of the amplitude of either the electric field or the magnetic field. So here it is, the intensity is proportional to the square of the amplitude of this vector field. So intensity will be the intensity of the polarized second polarized wave will be proportional to the square of the amplitude E prime. So E prime is E squared cos squared theta. So intensity will be proportional to square of the cosine of the angle trapped between the polarization direction of the electric field and the direction of the orientation direction of the analyzer. So you can very well see that if the angle is 90 degrees, then the intensity will go down to zero, because no light will be able to filter through this completely orthogonal state of orientation. So this law, intensity of a polarized light as it is made to pass through an analyzer, something that filters, extinguishes, that can extinguish a polarized light if it is aligned 90 degrees to the orientation of the electric field. This law is known as Mallieu's law, named after Etienne Mallieu. And so this is how you find. So how do you incidentally, what is the use of this formula? It's a very simple thing. You have a polarized state of light coming towards you. How will you know what is the plane of polarization? Subject it to an analyzer. Rotate the analyzer. at the angle where the analyzer will show you 0 intensity, you will know that the electric vector field is polarized to an angle that is 90 degrees to that. So that is the way you can identify the polarization orientation of polarized light. So this is one way of finding it. Now, polarization can happen. So this is one way of making polarization. I just described polarization happening through making light pass through a crystal material, calcite, quartz. These are various kinds of polarizing material. But polarization actually can happen in a far easier manner. And so this is what we shall now discuss: polarization by reflection. Let us now try to see. This is, I'm referring to a very simple conceptual case of reflection and refraction. So let's first try to understand. Here it is. So here is, look at the horizontal line in this diagram. This is a dielectric substrate. So let's say some transparent material, glass, let us say. It could be water as well, but glass, let's say. Above you have a first medium and below you have a second medium. The first medium is usually air medium, air to glass, and so this is the line separating this thing, the interface between the air and glass media. Now, light is incident on this glass medium. Now, this light is coming from the left direction and making an incident angle of incidence theta I. Right? This is the perpendicular, this is the substrate, this is the first medium, and this is the second medium. Now, at the point of incidence, two things will happen. There will be a reflected wave and there will be a transmitted wave. Had it been a perfect mirror, there would have been no transmission. All of the light would have been reflected. And had it been a perfect transmitter, like let's say clear thin glass, then all of the light would have transmitted. But usually what happens is that part of the light is reflected and part of it is transmitted. Now let us look at the incident beam over here. In the incident beam, there are two states of polarization. Let us try to understand this thing. Like I said, that any state of polarization can be decomposed into two orthogonal directions. So here we have some sort of a polarized light incident on this particular point, the point of incidence. The polarization state has been decomposed into two planes. The first plane is the plane of the page itself, right? So here, this is the light wave that is oscillating, the component that is oscillating on the plane of the page. And these black dots are representing another state of polarization, the orthogonal state of polarization. The actual polarization could be in any direction in space, but we have decomposed it into it, since it's a vector, we have decomposed it into two components. One component is on the plane of the page itself, and the other component is coming out of the plane of the page and then going in. So from this black dot, let us say, a wave is coming out, an oscillatory direction is coming out, and then it is going into the second black dot, then going into the page on the other side, and then it is coming up here again. So that incidentally is the way light wave propagates. Here we have got the electric field oriented in some random direction in space. We have collapsed it into two components. One collapse is on the page itself and the other collapse is perpendicular to the page. The perpendicular component is represented by these black dots, and the component that is collapsed on the page is represented by the wave itself. This is to be understood as the superposition of two mutually orthogonal wave trains. The other wave train that I have not explicitly drawn is represented by these black dots. One black dot means it is coming out. Another adjacent black dot means that the oscillatory state is going in, and like that. So now let us look at this thing. Of course, for all angles of any general angle of incidence, there will be an equal angle of reflection. Fine. But there is one very special angle. Now let us discuss this particular point. There is one very special angle where the reflected wave will carry away only the off the plane polarized waves, not the in plane polarized wave. So only off the plane polarized wave has been carried away at this very special angle of reflection. Not all angles of reflection will show this feature. Only a very special angle of reflection will show this feature. So this angle is known as the angle of polarization. So therefore, I did not write theta r over there. Normally we write theta I, incident angle, theta R, reflected angle, but here this reflected angle is happening at a very special orientation, and that orientation is also the orientation where only the off the plane polarized state is being carried out by this reflected wave. So that angle is the polarization angle. Part of the wave is also transmitted, and so that angle is the transmitted angle. You notice that when this value of theta p has been reached, the reflected beam will carry only off the plane of polarization, of the plane polarized waves, but the transmitted wave will continue to carry both states of polarization, which means, note one thing, at this point, two things happen. First, there is a reflected wave and a transmitted wave. That's the first feature. Now, all of the in-plane polarized, that's the first feature. The second feature is that all of the in-plane polarization is carried by the transmitted wave, but only a part, and no in-plane polarization is here on the reflected wave. But the reflected wave carries part of the off the plane polarized state, and so does the transmitted wave. So both the reflected and the transmitted wave will carry part uh, fractions of the incident of the plane polarized state, but the reflected wave here will not carry any of the on the plane polarized wave. So these wiggles, these waves that I have drawn will continue 100% from here, will move on 100% to the other side. But these black dots and these black dots, their intensity will be a fraction of the black dots over here. So that is what you have when you have polarization by reflection, and that takes us to Brewster's law. Let us see. We apply the basic concept of reflection and refraction and Snell's law. As per Snell's law, uh, refractive index of the first medium times the sine of the incident angle, sine theta I, will be equal to the refractive index of the medium into which the transmission has happened times the sine of the angle of transmission. Now, theta I is also equal to theta p, so I'm writing sine theta I is equal to sine theta p directly. Now let us look at this geometry. We are effectively doing geometrical optics now. Uh, to the right of this vertical line, there are three angles, theta p, 90 degrees, and theta t. All three of them will add up to 180 degrees. So theta p plus theta t is equal to, therefore, 90 degrees. So theta t will be equal to 90 degree minus theta p. Now here we have sine theta t. So sine theta t will be equal to sine 90 degrees minus the angle of polarization, and sine of 90 degree minus an angle will give you cos theta p. So once you have this thing, let's now look at the formula. Sine theta t will be replaced by cos theta p, and your formula will become ni sine theta p will be equal to nt cosine theta p. So ni sine theta p will be equal to nt cosine theta p. Therefore, sine theta p by cosine theta p will be equal to tan theta p. That will be equal to nt by ni. Usually, the first medium is air, whose refractive index can be approximated very well to 1. And so, nt will be equal to tan theta p. So this is known as Brewster's law. So if you want a perfectly polarized state, you just use Brewster's law. The refractive index of a particular medium is known. So from that refractive index, by the use of this formula, you can take the tan inverse of the refractive index, and that will give you the angle of polarization. Once you adjust your angle of incidence to the angle of polarization, this beam that you will get will be completely polarized, with containing only the of the plane component of the polarization state. So that is the basic principle of polarization by reflection. And if you have a state where, or situation where, the incident angle is not exactly equal to the polarization angle, then the reflected beam will be only partially polarized. It will continue to carry a little bit of the on plane polarization. It's only when you hit the angle theta p, the on plane polarized states will go away. They will not be allowed along this track, and you'll just have completely only the off plane polarization. So that is one state where you have, one way in which you can attain polarization by reflection. Similarly, you can also have polarization by refraction. This is the way Dominic Arago achieved it. Let's now try to understand this thing by using various glass plates as refractors. So here, in the previous system that we discussed, we just considered only one interface. It is as if that the depth of the glass interface was infinite. But if you now use alternative glass plates separated by an air gap, let us see what happens. So here is a pile of glass plates. Okay, so here is what happens. So the incident angle is equal to the polarizing angle. Therefore, the reflected angle is also equal to the polarizing angle. Now, when this state is achieved, here's another observation. At theta p, that is the polarizing angle, 85% transmission for polarization perpendicular to the plane of incidence. So, perpendicular to the plane of incidence means this is the plane of incidence. We are referring to the polarized state that is perpendicular to the plane of incidence. So if we go back to the previous diagram, so of the plane state, 15% goes this way, 85% goes this way. So the way to do this thing is to have successive filtration of this of the plane state. And so when you do that, this is what you have. Let's now try to see. We have this beam hitting this thing. A reflected beam is taking 15% of the plane polarization. 85% will be transmitted, 85% transmission for polarization perpendicular to the plane of incidence. So here it is. Then when it comes out, some sort of again it moves away from this 90-degree axis, and it comes here. So this line and this line are parallel to each other. This ray path and this ray path are parallel to each other, and therefore this angle will also be theta p. Again, what you will have here is 85% filtration of the 85% that has come out over here. 15% will go this way, and 85% of 85%. Here you have, after the first transmission, 85% coming in. Then another 85% has been filtered in here, 15% has been reflected. So this way you can have some sort of an enhanced polarizing state of the in-plane vibration. So you have used two plates to demonstrate the principle. The broader formula, degree of polarization for the in-plane vibration, will be given by this thing, m being the number of plates. M is the number of plates, n is the refractive index of the medium. This is the formula that you have, and so you can just work around this formula a little and write this like this. And so when m goes to infinite, larger the number of plate, greater will be the polarization that will happen. And so with a large number of plates, you will have greater and greater extent of polarization. So when m goes to infinity, you will have 1 by infinity going to 0. This term will go to 0 and p will go to 1. So the light is fully polarized by refraction with regard to the polarization state that is aligned to the plane of incidence. So this is the thing. Let's go back to the previous diagram. You have an incident beam, and this thing, 100% of the incident beam, the in-plane polarization is carried with the transmitted beam, but 85% of the off-the-plane polarization is carried with this thing. So with successive refractions, by using a set of plates stacked upon plates of refractive material stacked upon one another, you will be able to filter out these black dots more and more. So eventually, when you have done this thing with a large number of plates, only the in-plane vibration will stay. Ideally, mathematically, it will require you an infinite number of glass plates to achieve that state. So here is how it is. Okay. So now, since we have discussed, by the way, Professor Rajendra, can you please just confirm that you have been able to hear me through up to this stage, right?
Yes,
Yes. Okay, I
yes,
just
we can hear.
wondered. Okay. I just wanted to confirm that if everybody is on board or not. Okay, thank you for the confirmation. So now, yes.
Just a second. We can take 5 minutes break around 3:40.
Okay. Because I shall have to leave at 4:30. So, but we can take a break at 3:40. That is fine. Thank you. You'll just remind me by you please feel free to interrupt me at that time, right? Because I may not be able to keep track of the time. Thank you. All right. Okay. So now we come to a very strange feature of polarization. This is known as birefringence. Refringence is the old name of refraction. So birefringence is double refraction. Let us now try to see what we mean by double refraction over here. So some very special crystal material show this behavior of birefringence. They are calcite and quartz. Let us try to understand this thing. We have talked about polarization by refraction, and so now we shall have to look into this strange feature of double refraction in a polarizing material. So here it is, a calcite crystal. A calcite crystal can be chiseled into see, the thing about crystals is that they have neatly ordered layers of planes, atomic planes made up of atoms, because a crystal is an organized structure, an orderly structure. So if you chip off a little crystal material, it will form a very neat geometrical structure. So here we have got something like that. Let's say calcite. So this is calcite. Calcite is actually calcium carbonate, so carbon-based material, and quartz is a calcium carbonate, so calcium-based material, and quartz is a silicon-based material. So quartz actually is a very interesting crystal material. It shows various kinds of properties. In material science, it's a very interesting thing. Quartz. I mean, it shows so many features that we could exploit. One of these is this polarizing behavior. So let's now try to see. Here is natural light. So this crystal has been cut into a neatly ordered structure. It forms a parallelogram, a rhombohedron kind of a structure. And here we have something. So these two lines, this line, this face of the crystal and this face of the crystal, I'm just projecting this crystal on a paper. It's actually a three-dimensional structure. Let's now try to understand the geometrical layout of this diagram first. Carefully, let us try to follow. So here in the corner, I have put a schematic representation of what is going on. So first, let us see, natural light is incident on this interface, this crystal interface. This is air to the left, crystal material to the right. Now this is the perpendicular, this is the incident angle, and this is the reflected angle. And this is the refracted angle. Okay. So now birefringence means double refraction. So there will be two refracted rays for this material, two refracted angles, angle of refraction. So one is phi naught prime, phi being the incident angle. So the refracted angle is phi prime, but I have not just written phi prime, I have put two separate labels. O, not sorry, not O, not zero, O, phi O prime and phi E prime. Phi O prime is the angle of refraction for what is known as the ordinary ray, and phi E prime is the angle of refraction for what is known as the extraordinary ray. And so these two rays follow their path and then emerge from this crystal face back into air. So this is the situation that will happen. There's a little schematic diagram about what happens. This is the incident angle alpha. This is the refracted ray. After refraction, when it comes to this side, it again becomes alpha. But this ray path, and this ray path are no longer along the same track, although they are parallel to each other. So something similar is happening over here. This is the original ray path. This is the second refraction that has happened over here as the light ray moves from the crystal material to the air outside. And this is the ray path of the ordinary beam, and this is the ray path of the extraordinary beam, and both come out making an angle of phi with respect to the perpendicular that you have over here. Now let us look at the behavior of these two rays, the ordinary ray and the extraordinary ray. The ordinary ray submits itself to all the ordinary features of refraction. That is to say, it obeys Snell's law. And accordingly, since this is air, we are taking the refractive index of the first medium to be 1. So 1 into sine phi is equal to n into sine phi O prime. That is the behavior of the ordinary ray. Now, both the incident ray and the ordinary ray are in the plane of incidence. So as I said, the ordinary ray behaves ordinarily as per our expectation of geometrical optics. So in geometrical optics, we know that the incident beam, the reflected beam, and the refracted beam, they all lie on the same plane, which we call the plane of incidence. The incident angle is equal to the reflected angle, and the uh, n1 sine incident angle is equal to n2 sine refracted angle, Snell's law of refraction. So these are the behavior of the ordinary ray as we are familiar with. But the extraordinary ray behaves in a very different fashion. First of all, the extraordinary ray does not obey Snell's law. You can't apply this equation to the extraordinary ray. That's the first behavior. Second, does not generally lie in the plane of incidence, which means that this ray path that you have over here need not lie on the plane of the diagram, right? On the plane of the paper. It can come off the plane of the paper, go into the plane of the paper onto the other side. It can behave in this strange manner. So does not generally lie in the plane of incidence. And then the third thing, let us see. The third thing is that if light were to have been incident perpendicularly on this interface, then light would have followed this track straight with normal light. I'm talking about ordinary light, as we know. There would have been no refraction. And that is very much clear from this Snell's law behavior. If sine phi is equal to 0, sine phi would have been equal to 0. Therefore, phi O prime would also be equal to 0, which means that light would have gone on straight like this. But not so for the extraordinary ray. When phi is equal to 0, the extraordinary ray can still show refracting behavior. That is to say, it will turn from the original ray path. So that is what we have. Okay. So major difference between the E rays and the O rays. E rays are polarized along the plane of incidence parallel. Let's now try to understand this thing. Major difference. This is a very important feature. E rays are polarized along the plane of incidence, and O rays are polarized normal to the plane of incidence. Birefringence causes polarization. What do I mean by that? This is the original ray. that has come and hit this point. Thereafter, the original ray is refracted along two tracks. One, the track of the ordinary ray, and the other, the track of the extraordinary ray. Now follow this point a little attentively, please, that the natural light contains a random state of polarization in any direction. We can decompose that state of polarization into two orthogonal directions. One will be on the plane of this paper and the other will be perpendicular to the plane of this paper. What happens is that when light is made to pass through a birefringent material, what emerges will be this: the extraordinary rays will contain only the state of polarization on the plane of incidence, and the ordinary rays will carry the state of polarization perpendicular or normal to the plane of incidence. So here is the diagrammatic representation: polarization by double refraction, by refringence. So here it is: natural light is incident on this crystal block. The natural light contains both states of polarization, one on the plane of incidence as has been represented on this page, this wave, and the other perpendicular to the plane of incidence as has been drawn with these dotted black dots. Once they enter and undergo this birefringent behavior, the extraordinary rays will carry this, only the filter out. So this is a filtration process. They have been separated. The two polarization states which were together up to this point have now been separated from each other. The ordinary rays are now carrying only the perpendicular state of polarization, and the extraordinary rays will carry only the on plane state of polarization. So E rays, the oscillations are parallel to the plane of incidence, which means on this along the plane of incidence, and O rays, the oscillations are perpendicular to the plane of incidence. So you can now very well see the importance of this sort of behavior. Without too much fuss, you just make natural light pass through birefringent material, and immediately you will be able to filter out the E ray and the O ray. So that is what you have. So if you want to do quantum computation, one state will be like the message or the information contained will be in one state, the other state will contain the other state of in other encoded quantum information state in two different qubits. So that is what you have. But there is still a certain problem with this thing. The problem being that the two beams have emerged on the same site, right? So now you will have to use some mechanism by which the two beams will be separated from each other completely. That is, the two directions will be changed completely. They are still going in the same direction, although their planes of polarizations have been changed. Planes of polarization have been changed, but here they are still in the same direction. In order to do that, we need to understand a little bit of the geometry of calcite as a crystal material. Let us now try to see this thing. First of all, certain material features, the geometrical behavior. So this is an anisotropic material. What do I mean by anisotropic material? That physical properties depend on the direction. Example, graphite. Uh, I believe you are aware that graphite can be used as a material to manufacture tennis rackets. Tennis rackets undergo a high degree of stress when powerful serves are made with a racket by a tennis player. But the graphite material does not break on impact. But at the same time, graphite is also used in pencil lead. So there in pencil lead, graphite leaves a mark on the page, or I mean a paper. So there, graphite flakes off very easily from the lead point of the pencil. So what happens is that the tennis rackets are manufactured in such a way that it exploits the hardness of graphite in a particular direction, whereas lead pencils, they are not so much lead as graphite, So there they don't have to worry about that. So the pencil lead is there this property is not exploited, and as such graphite flakes off very easily, leaving a black mark on a page. So that is an anisotropic material. Calcite also has this sort of behavior, but in an optical sense. Now, what do I mean by an optical sense? That certain directions will behave differently optically with respect to certain other directions. For instance, uh, in certain materials, extraordinary rays and ordinary rays will travel with different speeds, although they are light, right? So when we talk about refractive index of a certain material, uh, glass material or dielectric material, transparent dielectric material, when we talk about the refractive index of a particular material is measured by the speed of light in vacuum divided by the speed of light in that material medium, right? So if ordinary rays and extraordinary rays were to travel with two different speeds, please follow this particular subtle point. If ordinary rays and extraordinary rays were to travel with two different speeds, then for each of them there will be a different value of refractive index, because refractive index is the speed of light in vacuum divided by the speed of a light wave in a particular medium. So excuse me. So they will have different speeds, and also the speeds will vary with respect to different directions. So that is an anisotropic behavior. So calcite is an optically anisotropic crystal material. So incidentally is quartz. So here we have some sort of some terminology is necessary. There is something known as optic axis. Uh, Symmetry of the optical properties is maintained about this axis. Along other directions, the symmetry may be lost, but along this particular axis, symmetry may be maintained. Now, certain crystal materials can have more than one optic axis, but calcite has got a single optic axis. Therefore, it is a uniaxial crystal. So optic axis implies it's a direction, not a particular. You don't draw a line passing through the crystal, and so how you determine the optic axis can vary from one material to another. We shall look at that feature. So now let us look at how calcite could be made to filter out extraordinary and ordinary rays. I'm sorry, just a minute. The mic dropped off. I hope you're able to hear me now. The mic just dropped off. I'm sorry. Okay.
Yes, we can hear you.
Okay. So calcite has got very clean cut cleavage planes. Cleavage planes are planes along which a crystal material can cleave easily. For instance, graphite has got very clean cleavage planes, and so in a pencil lead, the material flakes off along these cleavage planes. So calcite has got cleavage planes, very clean cleavage planes, very precise direction, and free surfaces lie along the cleavage planes. So cleavage planes are lines of weakness. So if you hit a material, the material will cleave, as we say, along those cleavage planes. So this is the geometrical layout of a calcite crystal. The crystal forms a rhombohedron. So this is calcite crystal material. Normal ordinary ray perpendicular incidence will just pass through, and the vertex angles, as you well know from school geometry, the four vertex angles will add up to 360 degrees, and two adjacent vertex angles will add up to 180 degrees. So here you have 108 degrees plus 72 degrees. You can see both of them will add up to 180 degrees. So the optic axis for a calcite material will be parallel to a line passing through the two blunt corners, meaning these two obtuse angles, corner A and corner C. These are the blunt corners subtending an obtuse angle. So the optic axis for a calcite material will be parallel to the line passing through these two points A and C. So, and then the other point that I have made in this diagram is that the light that will be incident normally on this line AB or this face AB will show no deviation for the ordinary ray, but the extraordinary ray can deviate from this line. Okay. Let us now see how we can, Professor Rajendra, hello? Hello?
Yes. Yes.
It's 15:40 as I can. Perhaps we should just take a break here because the next page will take a bit long to discuss. So I don't want
Yeah.
to.
If it's logical break, then we can break
Yeah,
for 5 minutes.
yeah. Logical break over here. We can just meet in 5 minutes time, right?
Okay.
So
Okay.
because yeah.
Thanks.
Okay.